MSc Environmental Sciences.
Excellent.
So I think, Anita ma'am, we can start the session.
Yes, ma'am. Sure.
Yeah, please. With your permission, Dr. Meenakshi, can we start the session?
Oh, please go ahead.
Yeah.
I'm ready when you are.
Yeah. Thank you.
A very pleasant morning to all, and good afternoon to Meenakshi ma'am. I, Anita Girdhar, on behalf of Department of Environmental Sciences and Department of Civil Engineering, JC Bose University of Science and Technology, welcome you all on the 4th day of Faculty Development Program on Green Technologies and Environmental Sustainability. Today we have 3 sessions in which 4 resource persons will be delivering their lecture. Let's start with the morning section by paying tribute to Goddess Saraswati with auspicious lamp lightning. May we have the lamp lightning? So with the tribute to Goddess Saraswati, let's begin the session. We are all aware that potable water, the elixir of life, is becoming scarce. The reason being growing population, urbanization, increasing pollution, and mismanagement of the existing water resources. During the last 3 days, among the various green technologies, we also learned about wastewater treatment technologies and water conservation practices which are being adopted. Today, to give an overview of the urban water management practices, we have among us Dr. Meenakshi Arora, Associate Professor of Environmental Engineering in the University of Melbourne, Australia. Having completed her MTech in Environmental Science and Engineering from Guru Jambheshwar University of Science and Technology, Hisar, and PhD from IIT Delhi, she joined University of Melbourne, Australia. She's a keen researcher, having received grants for over $15 lakh for various research projects from Australian government agencies. Her area of research includes water resource management, integrated water management, surface water and groundwater interactions, etc. She has supervised 15 PhD students. For her work in this area, she has received many prestigious awards, namely Future Women Leadership Award in 2017, WESCI Innovation in Engineering Award, Water Leadership Award in 2017, and Excellence Award for Internationalization of Research. I welcome you, ma'am, and request you to kindly take over and address the participants. Over to you, ma'am.
Thank you, Dr. Anita, for very generous and kind introduction. I'm delighted to be part of this faculty development program, and I should congratulate Dr. Renuka Gupta, yourself, and the whole team of JC Bose University to pull off such an event. Such events take a lot of ongoing work and planning behind the scenes, and I am quite appreciative of the effort you have put in through, regardless of being in the lockdown, working virtually. Each one of us, being university teachers, have shifted to online teaching, which is a humongous task by itself. So running a program like this on top of that is a huge achievement. So congratulations to all of you, and thank you for having me here today to discuss some of my research in urban water management. So I will share my screen. Just bear with me while I get this out of the way. All right. So are you happy for me to make a start?
Yeah, sure, ma'am.
Yeah, sure, sure.
Yeah, thank you. So I'll perhaps get rid of this. So I thought I'll give a brief introduction to myself, but Dr. Anita has done a great job in introducing me. Just to reiterate, I'm Associate Professor in Environmental Engineering at University of Melbourne. And I'm also Assistant Dean International with a focus to India, which is quite obvious because I'm really passionate to work with academics and researchers in India, being the place where I have studied and spent my childhood as well as early adulthood. And I have both teaching and research focus in doing so. And as part of that, I'm also director of Melbourne India Postgraduate Academy, which is mainly focused on PhD exchange. And at the moment, this program is running with 3 IITs, IIT Kanpur, IIT Kharagpur, IIT Madras, and IISc Bangalore. And the other important aspect of my current role is that I'm an academic lead for industry facing water security seminar series. And I have put a link here because we are also running it virtually now. So this is a monthly seminar now run as webinar, and it's open to everyone across the world who wants to attend. And at this link, you will find a video recording of all the previous seminars we have run. So if anyone finds it interesting, go have a look at this link. And if you wish to register for the next event. We had one just yesterday, so the next one is not until a month from now. So as you would have guessed, I have worked in India before coming to Australia, and I have done some work in Antarctica, a little bit different than urban water management, though. That project was mainly looking at removal of contaminants from groundwater and the soils. So in Antarctica, wherever the research stations are, the waste management hasn't been handled very well previously before the Antarctic Treaty came in. And we have a lot of legacy contamination. So my job was to try to contain that legacy contamination before it gets into the sea. My research interests are around water quality, contaminant transport and fate, and integrated urban water cycle modeling, which I'm going to talk a bit more today. It was mentioned that I have 15 PhD students, 10 have completed, 5 are still undergoing, and 2 of them are actually working in this MEPA program with a joint supervisor from IIT Kharagpur and IIT Kanpur. Where is the best place for this? And I teach both undergrad and postgrad courses in different research interests I just talked about. And I just thought I'll briefly take you through the university as well. So it's the #1 university in Australia, stands at 31 or 32. This year we have been given 31st rank just a few weeks ago. And it has quite large annual research investment, which means the university core business is teaching, but research is a very big focus. So for all of us, all the academics at University of Melbourne, we are required to spend 40% time teaching, 40% time doing research, and 20% time doing engagement and leadership. We have a 70,000 student population. 40% students come from overseas, and it's a large alumni community as well. Just to move on about Melbourne School of Engineering. So that was some information about the university, but Melbourne School of Engineering is Australia's first engineering school, and it was established in 1861. There is a passion for excellence and service to society. So that's the mission of Melbourne School of Engineering. not just publishing papers. So we have kind of tried to move away from the traditional academic outcomes, which have been winning grants, writing papers, to more towards impact. So what does your research influence in terms of application and knowledge transfer? So we have 800 PhD students in Melbourne School of Engineering, 4,000 master students, 9,000 undergrad students, and they are across all branches of engineering: civil, chemical, electronics, mechanical, computer science, and interdisciplinary engineering programs with specializations. We at the moment have 38% female students with 100 nationalities represented in that. And the school, Melbourne School of Engineering, is organized in 3 sub-schools. The first one is computer and information systems. The second is electrical, mechanical, and infrastructure engineering, which infrastructure engineering covers civil, environmental, and geomatics as well. And that's my school where I sit in. And I'm part of environmental group there, which is 11 academics in that group. And the third sub-school is chemical and biomedical engineering. So the outline of the talk today, I'm going to take you through the traditional urban water management model we have been using for over 100 years now, and some key challenges associated with that model. I'm just checking. Okay. I hope you can all hear me correctly. If there is any problem, please yell out and let me know. So some of the key challenges with the traditional model of managing urban water, some potential solutions, how we can deal with those solutions. And then I'll talk about the Melbourne's case in the form of case study. And I'll also briefly touch on impact pandemic is having on our water services and some key messages. So traditional urban water management, I don't think I need to spend much time here. You all know that we have been using a very linear system. As soon as the rain falls on our catchment, we try to take it through the drains and dispose it off in the stormwater drains or rivers or sea, whatever is the disposal for the catchment, without any use. So it's a very linear system. Rain comes, take it off as soon as possible. The other stream which comes to the catchment is drinking water. So drinking water comes to the households, we use it, produce the wastewater, send it off for treatment, and finally dispose. The key objectives of this system have been to provide a reliable drinking water supply and separate the wastewater from being in touch with the water supply. And to make sure that the second point is fulfilled, we have centralized wastewater treatment and disposal system so that the risk is managed centrally instead of multiple stakeholders having to manage that risk. And the other objective also was to rapidly transfer and dispose of stormwater so that we avoid the flooding in the catchment. And to be fair, all these objectives have been very well met by this traditional system. The problem is this system didn't consider the ecosystem health, mainly because the population was very small when these systems were designed, and our ecosystem could handle the kind of contamination coming into the system due to stream self-purification capacity. Now, as the population grows, that nature's capacity, the natural capacity does not grow with that, and we are seeing more and more problems. So if we look at it now, this water is not managed as a resource. Water was considered as a free commodity, which is available freely and infinitely, and we can use it. And planning did not address climate change vulnerability because climate change perhaps wasn't a thing 100 years ago when these systems were planned. And potential use of urban landscape was not realized. There was no realization that the communities and the habitations can become so dense that we might have to think about being more efficient in using the water available. The other key challenge, so the key challenge which is adding to those complexities or problems is that our population is growing. And it's not only just growing, most of the population is now tending to move towards the cities because of the opportunities cities present. So Melbourne is sitting at 4.5 million now, and there is a projection that it will grow to 7 million. And it's the case with and there is a projection which was made in 2009, so it's a bit old. Nearly 70% of world population is expected to live in cities by 2050. But even though it's old, this number must have only grown. It hasn't gone back. So what does it mean is there is going to be growing demand for water, and not just growing demand, that growing demand is going to be very concentrated in small city areas. And finite supply of fresh surface water is not going to grow. And sustainable urban growth is dependent on water. So there is no argument against it. If anyone has something to discuss, please raise your hand. I'll be very happy to talk about that. The other challenge is, so the challenge continues. It's not the other one. Next slide. So increased population is going to lead to growing water demand and wastewater discharges as well. So our problem is not just having a lot of demand for the finite water resource. Our other problem is we are going to have more and more wastewater being discharged into the streams, which make very limited source of our drinking water. So it's a reinforcing loop. We have less water available, we have more wastewater coming in, and we are discharging this wastewater into that water source, which means that we will need more and more treatment to meet the drinking water guidelines. And the other problem is with the stormwater, because we are building more and more impermeable surfaces in cities, there is increase in volume and peak flow of runoff with the greater sealed areas. And what does that mean is, if you consider an urbanized area, after a rainfall event, a lot of runoff runs through the streets, and due to high velocity of that runoff, you will this water is also going to erode the sediment and collect all the nutrients or petrochemicals or other toxicants in the catchment and take them all straight to the waterway. So increased frequency and severity of flooding is another problem. So if the stormwater drainage system can't carry the runoff, which happens to be generated after a big rainfall event, specifically due to the climate change, where we are seeing more severe rainfall, more extreme rain events, we are seeing more and more cases of flash flooding as well. So what are the choices with all these challenges, and how we have done in the past? So in the past, whenever we exceeded the demand, then supply, we build larger drains and accept the damage into the receiving water bodies. So that is one choice. The second is we try to think about some different ways of managing so that we don't just keep building larger drains and let our water bodies be damaged and not provide the ecosystem health they are able to provide. Instead, look for other ways in the catchment. And we'll talk about this a little bit later. So this slide actually just provides a visual of the urbanization effect on stormwater flows. So x-axis shows the time and y-axis shows the runoff flow, the volume of runoff. So the green line here is showing what's going to be the stormwater runoff if the catchment is undeveloped, for example, a forested catchment. So as soon as the rain starts to fall, there is always some base flow in the catchment from the previous rainfall. So you will start to see some runoff being generated after some time of the rainfall event. In the beginning, the rain which falls on the ground is going to be intercepted by the soil, okay, and it replenishes the soil moisture stores. Only after the soil becomes saturated, you start to see the runoff, and it peaks after a certain time and slowly declines as the rainfall stops. And when the rain has stopped completely, you still have some base flow because the soil moisture is going to, the water molecules are going to continue to travel down as well as horizontally. On the other hand, if it's a urbanized catchment, there are no base flows when there is no rain. As soon as the rain begins, you start to see the spike. And if the rain continues, you see big spikes instead of small spike. So what does this mean is when a large volume of runoff is gushing through, it is going to accumulate more pollutants along with it and also lead to soil erosion on the way. And when the rain stops, again, there are no base flows. So it has problem of flooding and deteriorating the water quality in receiving waters, but it has other problem as well. When there is no rain during the dry seasons, the streams are going to run dry because there is no base flow contribution from the groundwater. So these are some of the pictures from floods in Brisbane in last few years, and Kerala was no different in the floods a couple of years ago. The second challenge is the climate change. I'm again presenting an example from Australia, but many parts of India are going to experience similar situations. So this is a study done by CSIRO, and they looked at 3 greenhouse gas emission scenarios: low emission scenarios, medium emission scenarios, and high emission. I'm not going into the numbers, but at the moment, Australia is in high emissions bracket. Okay, and according to this study, by 2030, 2050, or 2070, these little pictures are showing the status of temperature change relative to now. So you see, there is a table at the bottom, the indicator at the bottom, which shows the blues or light yellow color means there is less than 1 degree increase in temperature. But with the high emission scenario, even by 2030, where we are tracking at the moment, we are going to experience 1 to 1.5 degrees Celsius increase in temperature. And by 2070, even if we reduce the emissions to low, which is highly unlikely, it is going to take a huge effort, but still we will be close to 2 degree increase in temperature. And in Western Australia, it's going to be above 2 degrees. So the projections are not very good. So temperature is projected to be growing or rising in whole of Australia. And the same study also looked at the rainfall projections. And here you will see all the greens and blues mean increase in rainfall in terms of percentage relative to long-term Australian average. And the yellow and orange going towards red means there is going to be reduction in rainfall. So again, at all the emission levels and at all the 3 timelines, there is a declining trend of rainfall except for Northern Territory region, which historically gets high rainfall and presents its own problems. But largely, the trend is drying trend for Australia and increasing temperatures for Australia in the future, which means we will be seeing more and more droughts. So these are the 2 pictures from droughts in Australia, and these are the 2 pictures from droughts in India. So both the countries share pretty similar problems in terms of water resource management. Just one more slide about Melbourne dams. So, and I'm going to talk about how Melbourne collects its water, but Melbourne has 10 storage dams and large catchments, and the rainwater is collected in those reservoirs from which we capture the water for treatment and distribution to the whole city for use. And this graph is showing 100 years of water storages in the reservoir. So how much water has been collected. So x-axis is showing from 1913 to 2017, and the y-axis is showing how much water was stored in all those reservoirs. So if you look at the first line between 1913 to 2000, so the average storage or average runoff was 615 gigaliters in Melbourne reservoirs. But then Melbourne went into a 13-year-long drought from 1917 to 2009. And during that period, the average of storage in those reservoirs fell to 376. So from 615 to 376 gigaliters, okay, close to half. And if you see from 2000 post 97 so far, so after this 13-year-long drought, there has been some recovery in the rainfall, but the long-term average between 97 to 2017, we still haven't recovered. It's still 416 gigaliters, which is 1/3 less than the long-term average. So what does it tell is that the climate change perhaps is posing a big challenge. We are having reduced rainfall, which means reduced runoff, high temperatures, more evaporation, reduced soil moisture, and less runoff. And the droughts are going to be more often and more extreme. The other problems are reduced base flows in the rivers, which means greater concentration of pollutants because there isn't enough dilution happening in the streams. Increased bushfire risk to water supply catchments. This is particularly relevant for Australia because we use the forested catchments where human activity is prohibited. So there is no human intervention. Water is collected from those catchments, stored in the reservoirs, and it provides very clean water source for supply. So more extreme, unpredictable climate events. So we are seeing that already, extreme rainfall events in 1 year and no rain in the next year. And because of that and increasing temperature trends, we are going to have peakier demand days in the summer. So if the summer becomes more extreme, it has implication on the peak demand, which means it has implications on the infrastructure size. An increasing population, of course, not only adds to numbers, but density as well. So the overall challenge we have in front of us is how do we provide adequate water services and protection from floods and droughts to our cities, which are subjected to multiple constraints like population growth, climate variability, and climate change. And we want to do it all in an environmentally sustainable and cost-effective manner. Okay, so it can perhaps be done if you have unlimited budget available to deal with the problem, and if you don't focus on the environmental sustainability. But we are at the brink of being unsustainable. Research shows that we already are operating at levels that we need 1.67 planet to meet all the demands we are posing today. So we need to be environmentally sustainable. So what does that all mean for water management? So the graph I just showed you about last 100 years of surface runoff to Melbourne reservoirs, where the long-term average is 615 gigaliters per year, but since 1997, it has only reached to 415. It tells us traditional rainfall runoff data is not a good predictor for the future, because we have always planned our future supply on the basis of what have we seen in last 100 years. Okay, and Australia has always taken pride in having long-term history of water use and supply information available, but it shows that it's just not a good predictor anymore. And climate variability means that we might see more of those severe events, leading to more intense floods and droughts, because 13-year drought is quite long and severe. No one predicted that the drought will continue this long. Previous droughts have been shorter in duration. So what we need moving forward is we need to have adaptive response that does not rely on the rainfall for water supply. So we just simply can't wait for rains to arrive and meet all our demands. We need to look for other sources. And it has ability to capture water when it's available, because it's not a new situation that flood comes and we have our cities inundated in water, and a few months later we don't have enough water to supply. So we need to develop systems where we can capture water when it's available. And the third is we need to utilize diverse portfolio of water sources to meet the demand. So Melbourne had to learn this lesson hard way, that we over rely on rainfall, and if it doesn't rain for a few years in a row, there isn't much alternate options we have got for the city. So we need to have some other water sources into the mix, so that if one fails, we can still continue. So we need adaptive response to climate change and demand uncertainties. So we need to, the response should consider climate change as well as the uncertainties associated with demand, which comes with the population growth. I'm keeping an eye on the chat box. There aren't any questions yet, but I'm happy to stop by if people have questions. Feel free to stop me in the middle and ask a question by raising hand or unmuting and asking the question. Is there any burning question so far?
Dr. Meenakshi?
Yeah.
We would like to have questions at the end of the session.
All right. Okay. Thank you. Then I'll keep going. All right. So one emerging solution for this problem, which can provide an adaptive solution to deal with climate change and growing demand, is the concept of one water. And people use different names for this. For example, integrated urban water management or water sensitive urban design. But what it means is that we use an integrated approach to plan and manage urban water systems, such as water supply, wastewater, stormwater systems, and groundwater in an integrated way, not as 4 different water services. So it aims, and this has historically been treated as 4 very different systems managed by different departments without much interaction at all. So IWM aims, number 1, to meet all the demands. That's what we want, that all the residential demands, industrial demands, as well as agricultural demands are met. But we want to do it in a way that minimizes the impact on natural environment and also maximizes the contribution to economic and overall community development by using less resources and producing less waste. It seems too good to be true, but how do we get around this? So the other thing I said is we need to diversify the supply portfolio, and we can only do that by supplying fit for purpose water. So we just discussed that we have wastewater available, which we dispose of. We have storm water, which we dispose of. So can we make any better use of these two streams of water, which are considered waste at the moment, but is there any resource value in that? And the third is that we have sea, for some cities, the coastal cities, seawater is another resource. Can we make use of that? And this picture actually just shows the concept of fit for purpose water supply. We really don't need drinking water to flush the toilets. That seems like the biggest scam to me when we talk about water shortages and water contamination issues, or for that purpose to irrigate the lawns and parks, unless it's the edible food crops. Such non-potable uses can be supplied either by rainwater or by recycled water. And this table shows a bit of key on how to decide which one of these 5 sources can be used to meet various end uses. So we have roughly 6-7 end uses, like we need to use water in the bathroom. Perhaps it's best to use the potable water, drinking water, because in shower you may perhaps ingest some water as well. In kitchen, definitely potable. For toilet, yeah, potable water supply is non-preferred for toilet. You can use rainwater, storm water, or treated wastewater. The same thing for laundry. For laundry, it's compatible use, but the preferred use will be if you have rainwater tank. That's good enough for laundry. So I'll let you read this in your own time. So what this fit for purpose approach will require is that we move from this linear system to a more integrated circular system. So the extra arrows on top of the linear system here are that instead of disposing this treated wastewater, we bring it back into the system for households, and households can use it for flushing the toilet, so it can be plumbed to the toilet and the garden tap, and in some cases to the laundry as well. And we can also generate energy by utilizing the sludge which comes out of the wastewater treatment process. If this is not acceptable in certain circumstances, this treated wastewater can be put back into the reservoir, which provides it greater dilution, and then it comes back as part of the water supply source. It's happening in many ways already, and I would say it's happening more so in India than in Australia, because in Australia we use reservoirs which are separated from the wastewater discharges. So therefore, it makes sense that we bring and perhaps make a decision of putting that treated wastewater in the reservoir. But in India, where wastewater gets discharged into a stream, which also provides the water source for the city downstream, it's happening indirectly, but we can do it more deliberately. The second one is that we start to use rain as it falls on the households by collecting rainwater from the roof in the tank, as well as rest of the rainwater which falls onto the pavements and roads and parks and green spaces, which gets collected as storm water, can be either treated separately or along with the wastewater, so that it becomes part of the recycled water loop as well. So this stock and flow diagram actually shows that we can have various water sources providing for these water uses, supplied using a fit for purpose approach. And these are our stocks of waters. So potable water coming in class A water tanks. So class A is used, so we use different classifications in Australia for the water treatment level. The secondary treated wastewater is considered class C. If you intend to use it for non-potable demands at households, it needs to be further treated through membranes to reduce the pathogen risk and the salt content. And Class A water is one which is permitted for use at households. And it can help to consider the constraints posed by demand and climate change, constraints on demand by climate change as well as population. So the implications though are, as you just saw in the previous picture, which I haven't fully explained, but it's quite easy to follow. But it's easy to notice that it's much more complex system. So if you are planning to use rainwater for certain end uses and then bring in the storm water, bring in treated wastewater, and you have some drinking water coming in as well, the system becomes far, far more complex. And there are several challenges or questions that need to be answered or explored before we can successfully implement these systems. The first one is, how do we predict the end use demand to plan for fit for purpose water supply? So far, cities have looked at average metadata from people's households, and they average out the demand for a community on the basis of population. So, and they just simply use that demand data to calculate for the projected population of this city how much water we need to supply. And that kind of estimation of demand helps them to ensure, number one, that that amount of water can be supplied, and secondly, that they have infrastructure with capacity to distribute and treat that demand. But if you start to use different water sources for different end uses, you suddenly need to have a very good handle of demand at each end use. So how much water people actually use in the bathroom, how much they use in the flushing of toilet, how much they use in the laundry. And that becomes a very complicated modeling exercise. The second question is, what is going to be the impact on overall energy use and greenhouse gas emissions? So water treatment and wastewater treatment are quite energy intensive processes anyways, but if you throw in recycling and stormwater treatment, the unit cost of treating the water and distributing it can be higher than the traditional water source. So it's important to understand how is it going to affect the energy use and greenhouse gas emissions. The third one is, how is such system going to interact with the existing infrastructure? For example, if you tend to use treated wastewater, which is high in salt than the drinking water, your wastewater stream is going to be more concentrated. Same goes for use of rain tanks, because if the water comes from the roof and zinc has been a problem for the water collected from the rooftops, your wastewater treatment plant is going to receive wastewater with characteristics it's not designed for. So it will still do a good job of removing BOD and nutrients, but perhaps not for other heavy metals and salt. And the other problem might be, depending on how much recycling is done, wastewater stream can be concentrated to the extent that it presents some hydraulic issues in the reticulation system. So it's important to understand the infrastructure layout and how these systems are going to interact with the limitations of infrastructure already in place. And looking at all those, there is going to be a shift in the cost. So is this proposed strategy cost effective? Is it socially acceptable? For example, in Australia, we can only use treated wastewater for non-drinking purposes, while Singapore actually just mixes all the water and they treat it wastewater to potable standard. So what is acceptable? What is the policy framework around those alternatives? And is it environmentally robust? So we just said that we want to do all this to make sure that we maintain the ecosystem services provided by our environment, and the solutions we are proposing, are they going to meet, get that tick? And yet another one, what is the best treatment train to provide the required quality? So we are saying wastewater can be treated to non-potable or potable standard, and the stormwater can be treated as well. But what is the best way to treat this to the level we are looking for? So this is an integrated framework for IWM, and I must mention that the questions I just posed, these are my research interests, and my group has been doing a lot of research in first 4 questions. The socially acceptable, I don't do social science research, but we just follow the policy guideline in our models, and number 6 and 7. So if anyone has any interest to talk about these questions in more detail, feel free to get in touch. So from the research we have been doing, it's important that IWM framework actually looks at all these 6 domains presented in the first row. So water balance, of course, is important so that we can have a demand supply balance. Water quality is important to make sure that the risk managed and there is appropriate fit for purpose supply available. And then energy and greenhouse gas emissions are important because increased energy input directly means increased cost, and cost is the biggest driver in decision making for which solutions can actually fly. But then there are 2 other boxes: social, institutional, and environmental. And what my research shows is that we have generally across the world only looked at the first 4 boxes, and we tend to leave out the social, public acceptance, public participation, equity kind of issues, as well as the environmental issues. And the main reason behind that is it's very difficult to quantify the social and environmental advantage or burden. So we have recently been using this different lens of water productivity, which means most recycling and stormwater harvesting schemes around the world fail on cost benefit ratio, because if you just look at is recycling or stormwater harvesting, which requires treatment as well, going to be less energy intensive or cheaper than the traditional water supply, and you do the cost benefit analysis on that basis, it's definitely going to fail, because answer is no. But if you include environmental and health benefits, they can be significant, but they haven't been considered properly. So we need to use a water security, water productivity lens, and it reflects the objective of producing more goods and services per unit of water used, minimizes social, economic, and environmental costs, and includes all the values we create and all the costs incurred or passed to another sector. So that is important. By moving on to recycling or stormwater, the value we create is cleaner environment, and the other value we create is less disease burden. So people will be healthier, they will perhaps take less sick days, and that improves the productivity. The other thing is we don't consider the cost incurred or passed to another sector. So when we, for example, do wastewater treatment or perhaps incinerate the sludge at the end, we are passing the contamination from solid phase to the air phase, or the the risk of heavy metals into a water body, which might then bioaccumulate into the fish, and then people consuming those fishes might get sick. So the cost of water treatment has been passed on to the health department or health sector. If we start considering all those costs and the values, this cost benefit ratio might start to look very, very different. And CSIRO, the same agency which I showed did projections for temperature and rainfall, did a multi-year study to quantify the social and environmental values. And if you use those figures, it shows very different picture. So if you use that productivity lens, the highest productivity gains occur from substitution, which is reuse, that you substitute the water of high quality with the lower quality without any treatment. For example, rainwater harvesting, use that to garden, water your lawns or flush your toilets. The other one is regeneration, which is recycle to non-potable or potable, depending on the policy framework of the site. And reduction, demand management. I'll talk about demand management in a second, but elimination of non-revenue water is also reduction. And there are areas around the world where non-revenue water is as high as 40%. So if we could eliminate those wastages, there will be highly productive gains. And this picture actually just shows some examples in each one of, those three categories. And this is a paper in Science. There is reference at the bottom by some of my colleagues. So talking about the case study in Melbourne and Melbourne's response to Millennium Drought. And I mentioned briefly, so Melbourne city is here, Melbourne CBD, and this whole area. So this is the Port Phillip Bay, where a large amount of treated wastewater gets discharged and some wastewater gets discharged into the Western Port as well. But the green areas on the top show the catchments which are protected from human intervention for water collection only. So we collect the water from these catchments, and these blue dots with the names attached to them, these are the 10 reservoirs where water is collected from these catchments and kept there until it's used, taken out and treated for distribution. So how does Melbourne water supply work? Melbourne's annual water use is around 420 gigaliters of potable water, because so far we have been distributing drinking water for every end use. Demand is going to grow to 600 gigaliters, that's the projection. And we have one bulk wholesaler, Melbourne Water, who is responsible for managing the all catchments as well as storages and the river health. There are 3 water retailers though, Yarra Valley Water, Southeast Water, and City West Water. They buy water from Melbourne Water, they treat it, distribute it to the users, collect the wastewater, treat it, and send it back into the environment. So the 10 storage reservoirs I just mentioned, they provide a total capacity of 1800 gigaliters. So basically we have roughly 4.5 years of storage capacity for whole Melbourne. And they are all interconnected. So if one reservoir is running low, it can transfer water from the other reservoirs. So most of the water catchments are forested and closed to public, and they drain into those reservoirs, and water distribution is largely gravity fed because the reservoirs are at quite high elevation and water is then distributed through gravity. So very little energy is used for Melbourne water supply, both for treatment and distribution. And very little groundwater is used, so 30 gigaliters per annum only, mainly at the farms where there is no centralized water supply. So the drought went on for 13 years, and government didn't realize that drought is going to go for this long. With the 5-year storage capacity available for Melbourne, they have always been able to deal with it. But this time, reservoirs fell to 30%. And that's when it was realized that we need to really look for other options. If it went on for another 2 years, Melbourne will run out of water. And that's when the two large infrastructure projects were put in place. One is the desalination plant to supply 1/3 of Melbourne's demand. And the other one was north-south pipeline, basically just to transfer water from irrigation district to Melbourne city to meet the urban water demand. Just for your information, north-south pipeline has never been used because both these projects were completed only after the drought broke. So we had big rainfalls. Desalination plant is being used now because we are in a moderate kind of drought again, but north-south pipeline is not used at all. But while we were building these treatment plants and the pipeline, which didn't even get completed in next 2-3 years when we needed it, demand management was a big thing. So there were a lot of awareness campaigns run throughout the country, including in Melbourne. The water levels were displayed on the billboards on the street. So you drive down the street and on the highway, you see on the billboards, it's showing you what are the water levels, what is the rainfall been in the last year or so. And on the basis of that, Melbourne only has water enough for next 18 months and now 12 months or whatever. So it was displaying very aggressively. And there was a lot of media campaigning, and there was 155 liter per person per day water use target, though before that it was 240 liters per person per day. So there were various water use restrictions from stage 1 to stage 4, and stage 4 meant that you can't put any water on your lawn unless you have a rainwater tank, and you wait. If it rains, you can water your lawn, otherwise you can't. And rainwater harvesting subsidies were provided to people so that whenever it rains, you collect that water. And efficient appliances were also advertised quite strongly. So that was a time when most households shifted to dual flush toilets. Almost all the shower heads in Melbourne households are quite efficient, which run at lower flow rate than normal. And water rating for dishwashers and clothes washers came in, and people can only buy highly water efficient appliances. The other ones are not available in the market anymore. But the surprising thing was all those measures for demand management, they led to 40% reduction in residential as well as industrial water demands, plus emergency reductions in environmental. So some of that 40% reduction came from emergency reduction in environmental release of water to streams. So there are minimum water flows which are required to maintain the ecosystem health of the stream. So there was a reduction in that as well. So there was emergency cut in how much water you leave for the environment, and it had its own damaging impacts because we lost a lot of flora and fauna as a result. But majority of this reduction came through the awareness campaigns. The other target was that we are going to increase the wastewater recycling to 20% by 2010, and Melbourne did achieve that target actually. And this 20% reuse has been achieved through use of this treated wastewater for industrial uses, for irrigation, as well as for a household non-potable use for greenfield sites. It's hard to retrofit the brownfield sites, but for all new sites, it's a requirement now to use recycled water. We call it a purple pipe. So water comes in, drinking water comes in through one pipe, wastewater gets out through the second pipe, and a third pipe, which is actually purple in color to ensure that there is no cross-contamination, that brings in treated wastewater, which is fit for non-potable uses. So some of these gains in water conservation are permanent and still hold steady. But in some cases, recycled water for irrigation declined, where farmers had access to potable water. Some of them went back. But the Millennium Drought actually provided Melbourne with the opportunity to develop a more integrated approach to water management. But the question is, what if there is another drought? One is the potential saving from demand management will not be as big as during the Millennium Drought, because all the saving which we got from efficient appliances is fixed saving, and we still have less than 240 megaliters liters per person per day demand now, because that saving has stayed permanently. But if we had to reduce it further, we won't be able to achieve 40% saving this time just by demand management. But any other city, if they want to utilize these principles, there is huge potential. The other thing we did is we put in the desalination plant, which is kind of which was seen as insurance policy because it was completed after the drought broke. But now, as soon as the reservoir levels fall below 60%, government orders water from desalination plant. So governments are better prepared. They're not going to wait for reservoir levels to fall quite low. So we are using desalination water as soon as there is decline in the level of reservoirs. The other thing is we are still continuing to work on diversified supply to ensure reliable supply under variable climatic conditions. Desal plant at the moment can provide almost 1/3 of Melbourne supply, but we are hoping to grow by 1/3 by 2050 anyways. So if we continue business as usual, we will perhaps need another desal plant in few years time, or we can continue to work on other sources of supply, or maybe move to treated wastewater to potable standard, because treating wastewater to class A or just fit for non-potable use means it can't be supplied to the brownfield sites. Okay, but if we could treat, because it needs a purple pipe and you can't rip off the whole city and put the infrastructure in. But if we could go from wastewater to potable, then there is no need of additional infrastructure, and it can be sent out to every corner, existing as well as new establishment. So that's where the research is happening in my group at the moment. So Australia uses recycled water for non-potable uses in all greenfield developments. That is a requirement now. And the other requirement is to install a solar hot water system or a stormwater tank on all new houses. So you either have to have a stormwater tank or you need to put a solar system. So solar system is to get some savings in the energy use. So either or both the systems need to be installed on any new building coming in. I'll briefly just touch on how pandemic is impacting on our water services, just how we are going on time. So it is one of the most critical PPE and indispensable weapon in fighting the disease. Most effective barrier to the virus as well, because washing hands is the prime requirement to deal with the virus at the moment. But we also know a large proportion of global population doesn't have access to clean water, so they are at greater risk of contracting the virus. And many cities have reported that the water use has gone up during the lockdown period, but many utilities are not in a position to supply that additional demand. And they are seeking people to use less water, which they don't know how, because as I mentioned, Melbourne went through this whole process of moving to using less water through efficient appliances and awareness, and also reusing or recycling where possible, which is possible through rainwater tanks to some extent, but recycling is not possible when you are in a situation already. The other one is the wastewater management during pandemic. So wastewater containing COVID may pose some transmission risk if not handled properly. So it's important that wastewater management and disposal is done with caution at this time, more than any other time. And most COVID patients are asymptomatic or experience just mild symptoms and remain at home, which means they don't get tested. There is significant risk of widespread distribution through sewers. So, but they are still contributing to virus through the sewers. And there are studies which show that virus can be found in the human feces up to 33 days after the patient has tested negative. So they might still have small dose of virus in the body, which they will be discharging into the sewer. So, and there is limited information on environmental persistence of COVID-19, but other coronaviruses, they can remain viable in sewage for up to 14 days. So unless the wastewater is treated properly and disinfected before discharge into the environment, the untreated sewage in the water body might mean there is active virus into the system as well. So the other one, atmospheric loading of coronavirus in water droplets from wastewater, like can virus move from wastewater into the air? There is no clear study showing that, but there are serious implications of consequent discharge of treated wastewater into wider environment if it's not properly treated and disinfected. And risk is even greater in countries where only part of wastewater gets treated. So basically, wastewater treatment is critical to provide a defense against the virus. And waterways are used as, so where wastewater gets discharged into the open sewers and get mixed with the streams, which act as sources of domestic water supply, can actually present risk. In some countries though, wastewater is being used to track fragments of COVID-19 to identify the hotspots of disease. And it is a quite proven method to track whether COVID-19 is present in a particular community or not. And it's this method has been used for previous viruses and also to track different kind of drug uses in different communities. So it's a quite proven, well-established method. We could also monitor the rate of infection over time in a wastewater catchment area to look for either if they're getting spikes or if the virus level in the wastewater is reducing, it might suggest that the population is now moving towards the recovery. So a robust wastewater management system can actually be an asset during pandemic as well. So what this pandemic is showing is a wastewater system can actually present opportunity to monitor and track the virus growth, as well as, if not handled properly, may present some risk. The other thing I wanted to point out is the stagnant water in the locked buildings. Due to the lockdowns, there are various buildings which are locked for months or weeks, and just like food that sits in the fridge for too long, water that sits in a building pipe for too long can also make people sick. So it's important to realize that organisms can go in devices like filters, water tanks, heaters, etc. And within pipe materials, water can accumulate unsafe level of heavy metals such as lead and copper. So if the building has been closed for too long, it's important when it opens, run the taps at least weekly if possible. But if it is not possible, running some shock disinfection to the plumbing or running some test is something to consider. So the silver lining of lockdown, there had been some studies or news showing that there has been improvement in the water quality of Ganga and Yamuna region, but that's mainly because all the industries are closed and there is no treated wastewater discharge. Can we maintain this status this way? Perhaps not. We can't keep the economy out. We need to work on how to keep the waste out. But there are other stories as well which show that coronavirus lockdown hasn't led to any improvement in water quality, mainly because the CPCB report highlights that the domestic wastewater from 97 towns across Ganges releases 35 megaliters per day. Only 1100 megaliter of wastewater is treated, and remaining 2400 megaliter wastewater goes untreated. And the industrial effluents only release 300 megaliters per day, 9%. So if you test a water sample just downstream of industrial effluent discharge point, you will see some improvement in the quality, but large fraction of it is coming from untreated wastewater, domestic sewage. And therefore, there are insignificant reductions in BOD and COD if you look at the overall stretch of the river. So the challenge is exacerbated by pandemic, a huge demand supply gap, but that can also be, as I mentioned, Melbourne experienced that during the drought, and many cities have been experiencing. South Africa, Cape Town ran out of kind of experienced their day zero last year. Large deficit in infrastructure capacity, both for treatment and distribution. We know that very well in India, and variable supply leading to significant health implications, not having enough water and having too much at another time, of course, causes problems and potential contamination of drinking water sources. But the nature of these challenges is not new. These challenges have always been there. It's a matter of how well we manage them so that they don't add to the challenge at a time like pandemic. So the key messages is that it's important to move away from linear system to more integrated circular system for all sorts of reasons. Demand management can be a powerful mechanism if done properly with community engagement. That is the most important part of that. Community participation and environmental sustainability are key determinants for sustainable solution. If you could quantify the benefits for those two variables, the cost benefit for most of the alternate water systems changes dramatically. The pandemic has amplified some challenges faced by water industry, mainly associated with the water shortage and pollution. And there can be very large disease burden attached to lack of water services, both with or without the pandemic, and we need to consider them. Economic shutdown has demonstrated reduced pollution level in several lakes and rivers. So we know what are the activities, where are the plugs, but it's a matter of figuring out a way, how do we achieve those in long term? And that's it from me. Happy to take any questions. And this is a list of some papers from the work I just mentioned today. If anyone is interested, have a look as well.
Thank you, ma'am. Thank you,
So I'll
ma'am.
perhaps stop sharing. Yeah, thank you very much. I'm happy for questions or discussion.
Ma'am, thanks a lot for such a wonderful talk on integrated water management and the diverse uses of available water resources that can provide water security. Can we have questions from the participants? There are certain questions. One of the participants, Suman, she says, in some cities, there is shortfall of drinking water due to population growth and unplanned urbanization. The problem is getting worse year after year, especially during summer season. In some cities, there is rainfall uncertainty due to climate change. So what will you suggest?
This is a great question, and this is the state in almost every city where water shortage is a problem. At the moment, I actually have a student doing her PhD and her case study is Bhubaneswar city. So what the scenario she is presented with is the city supplies drinking water, but not to every household. So there are some households which are not connected, or I must say, there are some communities which are not connected to centralized water supply and wastewater. So she is looking at utilizing rainwater tanks, not for each household, instead collecting the rainwater from each rooftop at a community level, as well as collecting the storm water from each household at a community level. Rainwater is quite dynamic, and it's not available throughout the year. But if you look at the data, if you can build in proper storage for rainwater, not only above ground but also below ground, it actually provides a good resource to add to the water supply. So that is one. So putting rainwater tanks and stormwater harvesting solutions are perhaps the first step. The second, which is a long-term and more difficult to implement solution, is looking at wastewater recycling. Why I continue or keep pushing for wastewater recycling is rainwater is a useful resource, but it's not available throughout the year. Wastewater is a stream which is available every single day. It doesn't matter if it rains or not. People are using water, there will be wastewater generated, and it provides multiple benefits. If it can be used to meet non-potable demands, which actually make up to 40% of total water demand, it takes away a lot of pressure from water resource. And secondly, it helps our waterways in a big way, because if you treat the wastewater, a lot of treated wastewater which gets discharged into the receiving water bodies gets diverted from the environment. So you are reducing the amount of nitrogen, phosphorus, and organic matter getting into the environment. So there is no single solution, unfortunately, but I think a combination of rainwater harvesting, stormwater, and treated wastewater is the way forward.
There's another question. What are the recent research going on to utilize wastewater for rural works?
So I am assuming wastewater for... No, that's fine. Thank you for the question. Sorry, can you hear me?
Yes,
Yeah.
Yes, we can hear you,
Dr.
Meenakshi.
Okay, so the wastewater for rural works, I understand that you mean wastewater for agricultural use. So what I was talking about during the drought, we have been treating wastewater to Class A standard, and that is suitable for irrigation of edible crops as well. Okay, so the 20% wastewater which gets recycled in Australia at the moment is largely used for irrigation, because we haven't been able to retrofit to the brown sites yet. Only the new developments which are coming recently, they have been receiving treated wastewater for non-potable uses, and rest of the treated wastewater is being utilized for irrigation, for food crops as well as non-food crops. So I think there is sufficient research which shows it can be safely used for irrigation. A lot of research at the moment is actually targeted around use of treated wastewater for drinking purposes.
Ma'am, I have a question here. Like you said, we can use treated wastewater for irrigation purpose. So when we treat wastewater, there might be certain inorganic components there which would not be treated by the conventional treatment process. So when, like heavy metals, so when we irrigate those crops with that water, won't these heavy metals enter into our food chain?
That's a great question. Actually, I must have clarified. So when I say wastewater, I mean domestic wastewater. So if it's a domestic wastewater, it won't have large concentrations of heavy metals. And in Australia, we do spend a lot of effort in making sure that the domestic wastewater is not contaminated with the industrial waste. Industries are required to pre-treat the waste before they can send it to domestic wastewater treatment plant, or they are sent to a separate, like there are separate sewage treatment plants for industry versus domestic. So for recycling, for irrigation as well as non-potable reuse, I suggest separating the domestic wastewater from industrial wastewater.
Okay.
Because domestic wastewater can also bring, you might argue that you can't stop someone dumping in a box of paint into the domestic sink, for example, but with the large volume of wastewater turning up, there is a lot of dilution which happens. So the concentrations are not in the range where they will be presenting any challenge for reuse.
There's another question. It's related to coronavirus. Like coronavirus can survive in water too. So is the chlorine treatment for drinking water safe to make it virus free?
Yes. So what I said is it can survive, but in wastewater, what happens is if there is a robust wastewater treatment plant and a water treatment plant, it won't be a problem. But there is a potential threat if the wastewater treatment is not fully operational. If part of sewage gets its way into the water body, which also acts as source of water supply, it presents a challenge that chlorine dosage required might be higher. But that is also not a big concern because water treatment plants look at residual chlorine. Okay, so if the water gets through a wastewater treatment plant or a water treatment plant, it will be killed through the disinfection process. The problem is if there is a population relying to meet their water demands by fetching water straight from the stream, for example. So if the water is consumed without the disinfection process, it will present a threat.
Do we have other questions from the participants? Any more questions?
The participants can unmute themselves and can ask the questions. Anita ma'am, I think there are no more questions from the participant side. So you please proceed further.
Ma'am, I have another question. Like you talked about integrated water management system, where we use different sources. We integrate the different storm water, rainwater, treated water, and all for various diverse uses. Like this could be effectively done in the the urban areas which are coming up, like in the existing framework which we already have, the old cities. I mean, it would be not possible to do that integration. So what do you suggest there?
Okay, I think I should have perhaps clarified. That's what I mean by greenfield sites. Greenfield sites are the new upcoming areas where the whole water infrastructure is being put in place, and you can actually put in the purple pipe for treated wastewater as well as storm water. And the brownfield sites are the sites which are already established. And I already highlighted that challenge. That is a real concern, that treated wastewater distribution to a brownfield or existing site is just cost prohibitive. It becomes too expensive and too disruptive. So we are at the moment using treated wastewater distribution only for greenfield sites, and that makes the irrigation biggest user. But for the brownfield sites, Victorian government ran a subsidy for people to put a rainwater tank, for example, at their households. And now 35% Victorian houses have a rainwater tank. So rainwater tanks are quite easy to implement, even in the brownfield sites, but treated wastewater distribution is at the moment confined only to greenfield sites. And that's why I'm proponent of moving to treated wastewater to potable reuse, so that we can get away with this problem of not being able to retrofit. It will just not require retrofitting then. We just put the water into the same distribution line.
So it means that in the present scenario, in the urban cities where we are living right now, rainwater harvesting is the only solution.
Rainwater harvesting is the solution. The other option is the grey water reuse. I didn't talk too much about the grey water reuse because in Victoria, where I come from, but perhaps that shouldn't have stopped me from talking about it. Grey water reuse is still possible at household level, just like rainwater tanks, and there are small grey water treatment systems available as well off the shelf, which you can just buy and channel your grey water through it. It will treat it for non-potable reuse. But it's still seen as carrying some risk for the stakeholders, and it's not very widely adopted. But grey water reuse is another one which can be done at household level.
We have another question from the participant. The farmers in Australia faced dire drought emergency. Do you think is it a water issue or a water management issue? And what do you have to say on this?
Okay. If it's a particular instance when farmers are in a drought situation, it can be water issue. But I would say largely in agriculture sector, we are suffering from water management issue. We are failing on being efficient, because only up to 40% or even less than that of water supplied is used by the plant at the end. A lot of it, there is a lot of inefficiency in irrigation water use. 70% of whole of the world water gets used for irrigation, and it's a very inefficient system as well. So climate and water availability has a role to play for the irrigation sector, but I think water management has a huge role to play as well.
Still another question. How can the circular system of integrated urban water management be implemented in India in an economical way?
Okay, that is again an interesting question. I don't know if I have an easy solution for that, because let me pose it in another way. The Ganges Action Program was initiated almost 30 years ago, and since then this program has changed its name as the government's changed. And I think it's no-brainer that for a river, the problem is industrial waste discharges as well as domestic sewage. And the CPCB report, which I was just mentioning, actually tells that 2/3 of waste from all the 97 cities combined gets discharged into the river untreated. So the question is why we haven't yet managed to make sure that no untreated sewage gets into the river. So it's a similar question. How can we implement integrated urban water management system in India? I will argue if there is a desire, it's easier to implement in a country like India than in Australia, because in Australia we already have a wastewater treatment system which works for treating the wastewater very well. So it's a load of legacy to dump and build a new treatment system which can take us to the next step. But in India, we already have 2/3 sewage going untreated. So we need to somehow find a way to capture that sewage and treat it before it gets into the nearby river. So while we need to do that task, it's pretty much like a greenfield site for wastewater treatment in India. We have to start the process so we can actually take it to one step forward and treat it for at least non-potable standard, so that instead of putting it into the stream, we can make use of it. So I know it's not an easy solution, but the thing is, if there is no legacy in many cities, so it's in a way easy to pick up the innovative concept and take it to the next step.
Niharika Kaushik, she says, should water be considered a commodity now?
We are already considering it a commodity. I will tell you another little incidents. Last year, when I was going to IIT Kharagpur for my project, on the way, I always kind of fly to Kolkata and then take a taxi. In Kolkata, there are large wetland systems which feed on domestic waste. Okay, and someone from the fishery department was showing me off their wetland system and very proudly telling us that because we use our domestic sewage, we don't have to provide any food to our fishes. They just feed on this waste coming from households. And that therefore, in West Bengal, we can sell the cheapest fish in the world. And we asked them the question around the heavy metals and other stuff and bioaccumulation. And they said people are not getting sick. But then they all were drinking Bisleri water. They were all drinking bottled water. So water is already being treated as commodity. And I always wonder, in India, most people rely on either bottled water, or they put an RO or AquaGuard, some sort of filter at home. And if we actually start looking at the combined cost of all those systems, which people are putting at household, perhaps it will be cheaper to put a centralized system which can provide people enough trust to drink that water coming out of the tap and not having to spend money on either buying bottled water or putting their own treatment systems. So water is already, to me, it sometimes seems like water has become such a commercial commodity that so many businesses will get out of the market if we did solve this problem. So it's a matter of putting that business case in a way. I'm not sure if I have answered your question, Niharika, but I think it is already being treated as a commodity by some big businesses, and it is going to hurt them a lot if we try to solve this puzzle. And that is part of the problem. We are still suffering with water management issues.
Yet another question. What can be done to a village where water is arsenic contaminated and does not have pipeline water connectivity?
Mm-hmm. I actually did work on arsenic issues in groundwater in my PhD. So there are for the arsenic, the only solution is, if you can, don't drink that water, or you just remove arsenic from that water. But UNICEF did come up with quite a range of small scale household filters, which can be either used at household level or at community level. But if there is no centralized water supply, I think those kind of filters are the only solution to remove arsenic, because arsenic is pretty deadly, and it has created a lot of problems in West Bengal. And that is another classic example, actually, of shifting from one source to another. In West Bengal, the basic reason of moving to groundwater or hand pump water from the surface water was that streams and rivers have become too contaminated. So perhaps it's easier to shift to groundwater without realizing that contains a lot of arsenic. And that wasn't realized until 20-25 years of use, when people actually started to show symptoms of arsenic toxicity. But yeah, if there is no centralized supply available, the only solution is that you use some sort of filters to remove arsenic.
Any other questions? So I think all the queries have been taken care of. And thank you, ma'am, for patiently answering all the questions. I would like to invite Dr. Renuka Gupta, Chairperson, Department of Environmental Sciences, to propose vote of thanks.
Thank you, Dr. Anita. It was lovely to interact with you.
My pleasure, ma'am.
It was a really very interactive and wonderful talk. I'm very humbled to say a thank you to Dr. Meenakshi Arora for sparing her precious time for being with us in this program. I thank you for making excellent presentation and making the talk meaningful, interesting, informative, and very much interactive with the participants. You very rightly explained about traditional urban water management key challenges associated, and then shifting to the integrated urban water management depending upon fit to purpose approach. Surely we can manage the water demand and supply with finding out the right purpose and right type of water for it. Thank you for sharing the valuable knowledge on the very relevant topic of the present scenario, and thank you for being with us today. Thank you very much.
Thank you, Dr. Renu Gupta, for inviting me today. I thoroughly enjoyed talking about this, and thanks to the participants as well. It's been a very patient and engaging audience today.